U.S. Representative Anna Paulina Luna has publicly urged NASA to release previously unreleased images of the interstellar comet known as 3I Atlas. This comet has captured worldwide attention because it is not just a typical comet from our solar system. It is a rare visitor that traveled across light years from another star system to enter our cosmic neighborhood. NASA first detected 3I Atlas over the summer using the Atlas Survey Telescope in Chile, a telescope designed to spot fast-moving objects across the sky. Soon after, observations confirmed that it was an interstellar comet, a true traveler from beyond the Sun's influence, moving faster and with a trajectory unlike any ordinary comet or asteroid. What has truly stunned scientists is that 3I Atlas appears to have executed a deliberate braking maneuver, something completely unprecedented in cometary science. NASA's Jet Propulsion Laboratory reported that the comet exhibited measurable deceleration relative to the Sun's gravitational pull. Even more intriguing, the object showed non-gravitational acceleration components, forces that cannot be fully explained by known natural phenomena such as solar radiation or outgassing. Astronomers first noticed that its velocity did not follow the expected path for a simple hyperbolic interstellar trajectory. Instead of passing through our solar system passively, its speed appeared to slow as if some mechanism were applying brakes. This deceleration caused the trajectory to deviate from predictions based solely on gravitational forces. Radial acceleration measurements indicated roughly 135 km per day squared, while transverse acceleration was about 60 km per day squared. These unusual acceleration components hint at an active process, something beyond what standard cometary physics would produce. Adding to the mystery, the comet's tail sometimes reversed direction, pointing briefly toward the Sun, a behavior extremely rare for comets, which usually eject dust and gas away from solar radiation. This braking phenomenon is particularly compelling because it suggests purposeful behavior rather than passive, natural motion. Scientists are now questioning whether this might imply artificial propulsion or some form of engineered maneuvering. The braking occurred roughly 203 million kilometers from the Sun, just inside Mars' orbit, a region where solar forces are significant but not overwhelming. For any active intervention to occur in this zone, precise timing, energy, and control would be required, hinting at intentional navigation rather than random drift. If 3I Atlas is indeed adjusting its trajectory, it could linger longer in the solar system, change its exit vector, or even move toward a target region. This behavior challenges conventional comet science, which has long assumed that interstellar objects passively drift through space. Even if a natural explanation eventually emerges, the braking and non-gravitational accelerations force astronomers to rethink how interstellar visitors are observed and interpreted. The discovery has implications not only for physics and astronomy but also for planetary defense and space exploration planning. Future interstellar objects may need to be treated not just as curiosities, but as bodies that could display unexpected, purposeful motion. The braking of 3I Atlas serves as a potential, techno-signature, signaling behavior that warrants rigorous verification, continuous observation, and detailed modeling. Beyond its unusual motion, 3I Atlas has revealed remarkable insights into its composition and origins. Spectroscopic and infrared observations show that it has an ice-rich nucleus dominated by carbon dioxide, with smaller amounts of water vapor than typically found in solar system comets. This unusual chemical mixture suggests that 3I Atlas formed in a colder, more distant region of its parent star system, possibly near the carbon dioxide sublimation line, far from the warmth of its star. Data from the James Webb Space Telescope and the SphereX mission indicate that it is an ancient interstellar body, potentially older than our own solar system. Dynamical modeling suggests that 3I Atlas was likely ejected from a star system in the thin disk of the Milky Way, possibly by gravitational interactions with a giant planet or a binary star system. Its long journey through interstellar space may have lasted billions of years before it finally entered our solar system. The comet's size remains uncertain, with estimates ranging from 3.5 kilometers to as much as 11 kilometers in diameter, complicated by the presence of a dense, dusty coma surrounding it. Polarimetric studies reveal light reflection patterns not typical of solar system comets, suggesting it may belong to a class of objects previously unseen. Its trajectory brought it from the direction of Sagittarius, moving nearly aligned with the plane of the inner solar system, a tilt and retrograde motion that make its passage even more intriguing. 3I Atlas passed close to Mars and reached perihelion at about 1.36 astronomical units from the Sun. After perihelion, deviations from predicted paths became more pronounced, with both radial and transverse accelerations that challenge standard cometary models. Some researchers argue that enhanced outgassing could explain these motions, especially given the high carbon dioxide content, but the scale, directionality, and lack of corresponding debris complicate this explanation. Tail morphology added another layer of mystery. While normal comets form tails that point away from the Sun, 3I Atlas displayed sunward plumes early in its journey, suggesting directional ejection or a possible active process. Some astronomers have speculated that these anomalies might hint at an engineered origin, involving controlled deceleration and trajectory adjustments. Others caution that comets can behave unpredictably and urge restraint before concluding anything extraordinary. Regardless, 3I Atlas offers a unique chance to study material formed around another star, potentially revealing insights about comet formation, chemical evolution, and interstellar dynamics. Its journey challenges assumptions about passive motion in space, suggesting that interstellar visitors may sometimes exhibit complex or purposeful behavior. High-precision observations, tracking, and computational modeling continue to study its light curve, dust and gas emissions, tail structure, and acceleration vectors. Even if ultimately natural, its unusual behavior will influence how astronomers detect, track, and interpret future interstellar visitors. This event reminds us that the solar system is not merely a static laboratory of passive objects. It is dynamic, with rare and unexpected phenomena capable of defying expectations. 3I Atlas may be the first of many interstellar objects to display unusual behavior, from braking to trajectory adjustments, signaling that interstellar space is not entirely silent. Its braking, chemical composition, and trajectory deviations mark a turning point in the study of small bodies and interstellar astronomy. The observations encourage new approaches in survey design, detection of non-gravitational acceleration, and analysis of anomalous behavior. Philosophically, 3I Atlas challenges our perspective. Objects from other star systems may carry stories, chemistry, or perhaps evidence of engineered motion across the interstellar gulf. Its passage transforms how humanity perceives interstellar visitors, not merely as distant points of light, but as actors capable of surprising, and possibly purposeful, motion. In conclusion, whether natural or artificial, 3I Atlas represents a new frontier in observational astronomy, planetary science, and astrobiology, emphasizing the need for continuous monitoring, refined models, and openness to unexpected